All right, today we're going to begin by connecting our last piece of the puzzle when it comes to mole conversions. You're going to need your periodic table, your mole roadmap, and then finally a calculator. So we've introduced two styles of conversion factors so far. We've used Avogadro's constant to relate how many molecules or atoms are contained within 1 mole of a substance. And then the other option was the molar mass. And again, we can't define an actual number for that unless you know what element or compound you're discussing, because each element and compound has its own unique molar mass. And that again relates to the mole. So the last thing we can do is relate molar volume, so volume meaning space, in terms of a gas. And so if we weren't kind of in this format, we would spend more time talking about states of matter, but that time just isn't going to present itself. And so when we take a look, we can look at a gas under what's called STP conditions. STP stands for standard temperature and pressure. So if we were able to put a gas at this standard temperature and pressure, meaning 0 degrees Celsius, and then standard pressure is 1 ATM. ATM is not standing for like where you go to get your money from the bank. It's talking about atmospheres of pressure. And so when we look at barometric pressure in the atmosphere, that helps control our weather. As you go up in elevation, you have less atmospheric pressure than as you go down in elevation. And so if you standardize that pressure and that temperature, then any gas, doesn't matter if it's an element, compound, what the molar mass of it is, it will always occupy 22.4 liters. And so again, that's for 1 mole of any gas. So we have that conversion factor that we can then use, which would be again this piece here. And if you look, it's on your roadmap, ready for you to use. So we're going to dive right into a set of examples then. So in our first example, it says to convert 5 moles of hydrogen, and the formula for hydrogen, because it's diatomic, is H2 to liters. So we have our given here. It tells us that we have 5 moles, and we can include the what, and we need to change it to liters or volume. So I can go ahead and write this out, 5.0 moles of H2, and they want to know how many liters that's going to take up, how much space. So again, we have that 22.4 liters is to 1 mole. So based on how this problem is set up, we have moles to begin with, therefore 1 mole needs to go into the bottom, and 22.4 liters will be the numerator. Moles will eliminate, so mathematically what we need to do is multiply it out. When we multiply it out, we get 112 liters, and that's going to be hydrogen. Okay. Moving on to another example then, working with this molar volume conversion. This one has a little bit more going on with it. It says convert 2.2 liters of ammonia gas, the formula for ammonia is NH3, to grams. So the first thing I can see is that my given is this 2.2 liters of ammonia, and it wants to know the mass of it. And again, we measure mass in grams. So I can start with what I know. So 2.2 liters of NH3. The only direction I have, and if you follow your roadmap, the only thing we can do with liters is convert it to moles. Because this one starts with liters, 22.4 liters will be in the denominator or the bottom, and 1 mole will be the top portion of this particular conversion. That gets me to moles. The last thing it wants is it doesn't want moles, we need to get to grams. So if you take a look at your roadmap, to get to grams, you need to know the molar mass. So we're going to go ahead and use our periodic table to calculate the molar mass of ammonia. When we look at our formula to do our inventory, we have 1 nitrogen and 3 hydrogens. Nitrogen's molar mass is 14.01. Hydrogen we round off to 1. So if we multiply and add these up, we get 17.01 gram per mole. So when we go to add this second step to our problem, We need to make sure units line up to cancel. So 1 mole will be the bottom part of my conversion. The mass is what's going to go in the top, and I can go ahead and eliminate those. So these are a lot like the problems that we kind of started the week out with. So how many steps you need, 1, like up above in example 1, or 2, like here in example 2, it's all based on what unit you start with and what unit it wants you to end with. So this step, because we went from liters to grams, required 2 steps, versus if you only convert to something to a mole or go from mole to something else, that's always done in 1 step. So you can take 2.2 divided by 22.4 times 17.01, or you can take 2.2 times 17.01, then divide out by 22.4. When you solve, you get an answer of 1.67 grams, and this is ammonia. Okay, so I have one last example to work with this particular style conversion factor. So it asks, what is the volume of a sample of nitrogen dioxide gas, NO2, that has a mass of 29.3 grams? In this problem, then, you can see we're starting out with 29.3 grams of this NO2. It wants to know what's the volume. So you have to be careful with that. Because we're starting out with mass, the only thing you can do with mass is you must convert it to moles using molar mass. Again, follow your roadmap. So we have NO2. 1 nitrogen, 2 oxygen. Nitrogen again is 14.01. Oxygen rounds out to 16. Multiply and add everything up, and you get 46.01 gram per mole. So that's the first piece, because I need to get those grams to eliminate. So 46.01 grams will be the bottom, and 1 mole will be the top. I can go ahead and eliminate those. Now we need to get to volume. Volume is liters. If you take a look at your roadmap, the only way you can go from moles to liters is to use that molar volume conversion. That's the 22.4 liters per mole. I'm currently at moles, so 1 mole will go in the bottom, and 22.4 liters will go in the top. I can see that all my units cancel out, and I'm at the unit it wants me to solve for. So again, you have your 2 options on how to solve: multiplying and then dividing, or dividing then multiplying. Either way, you should end up with an answer of approximately 14.26. We now have liters, and this is nitrogen dioxide. So these are your 3 examples. You can then use these to help guide how to solve those 3 practice problems below.